Thomas Schonzart, who is the recipient of the ACA, the 2024 ACA Martin Buerger Award for his contributions to the understanding of the structural science of the F-block elements. The Buerger Award is presented to the researchers who have made notable and distinct contributions to the areas of broad interest to the ACA, not just structural science. It's very fitting that Thomas receives this award. Buerger was a mineralogist, and Thomas's research generates many new synthetic heavy element minerals, or mineral-like compounds. Sort of true. Early on, it's changed over the years. And it's through this research that has expanded our understanding of the chemistry of these challenging compounds and elements. His work has had a significant impact on actinide research throughout the country and internationally. Today, he will tell us about his race against time, crystallography and the outer limits of the periodic table. But before that, I'd like to present him with the Buerger Award.
All right, everybody can hear me okay? Yes. We're good? All right, well, first, I'd like to thank the award committee for this honor. It's particularly special because my PhD advisor, Jim Ivers, is a name probably well known in this room. He won it about 20 years ago. And so to see your name in the same list as your advisor's name is really, really cool. And the other thing is Buerger invented the precession camera. And I'm probably one of the last graduate students to use a precession camera. So Jim had Weissenberg cameras and precession cameras and the whole works. And I remember the first time, we had a dark room, so like we really used the real camera. And I remember I took my first photo, showed it to Jim, and he held it up to the light. And he said, "This is the worst photo I've ever seen." So on that note, let me get started. So as my title implies, we're going to be racing against time to characterize compounds that contain elements that are highly radioactive, and that radioactivity destroys the samples pretty quickly. And so the reason we want to do this is multifold, and I'll go through that during the talk. But if you just look at the front of this, my first slide, this looks like what everybody else in the room does. I mean, we've got beautiful crystals, nice red crystals and pink crystals and blue crystals. It's the elements that are in these that make this unusual. So this is a plutonium-4 compound. It's actually a plutonium-4 coordination complex. That's an americium-3 coordination complex. And in reference to the mineralogical work, this is a plutonium-3 borate. This one will actually hang around for very long periods of time. These will only last days, and I'll talk about ones that are much shorter lived and why you might want to go through the work to do that. So my group does a lot of different things, but at the core of it, we study structure and bonding. We make new things that have not existed before. We try to grow crystals as best we can to determine their structure. We do a lot of quantum mechanical calculations these days. And the reason is the electronic structure of heavy elements is so complicated that there's no hand-waving argument that you can use to explain the bonding of these compounds. One of the things that I'll close out this talk with is our segue in the last decade or so to high-pressure crystallographic studies, which when you combine the challenges of that with the challenges of highly radioactive elements, it becomes very technically difficult work to carry out. So even though we ask really fundamental questions, you could imagine that when you're working with an element like plutonium, this segues really nicely into many different areas, including developing crystalline solids that would, for instance, trap plutonium on geologic timescales and prevent its release in the environment, recycling used nuclear fuel, which has now undergone a renaissance, and many, many other areas that we currently work on or have worked on over the years. So what makes this work different, there's actually many things that make this work different. So the first thing I want to talk about is safety. So the irony is that you expect if you're in a laboratory with macroscopic quantities of highly radioactive elements that you're in an unsafe situation. And the fact is it's the exact opposite. It's the safest place you will ever be in your life. You are breathing the cleanest air you will ever breathe in your life because there's no other way to do it. And so if you're mounting a crystal, for example, and this is me back when my students would let me in the lab, mounting a berkelium sample, I'm wearing a lead vest, I'm double gloved, the inner layer of gloves is taped to my lab coat, I'm breathing through a respirator, and I need a set of cold hands. This is Shane Galley, who's now a professor himself. He's also similarly garbed, and that's our radiation safety officer breathing through a respirator as well. And that's because the real risk with radioactive materials is not what you think about with gamma rays blasting you from a distance. The real risk with the vast majority of them is an inhalation hazard. And that's the reason why the air in my laboratory is very, very heavily filtered through a multitude of different filters in order to prevent any sort of inhalation risk. But sometimes you have to go well beyond just that. So a few of these isotopes, californium-249 in particular, are strong gamma emitters. So that's a 3,000-pound lead wall that's wheeled up in front of a glove box. Because the other thing is, under these sorts of situations, you can't, it's a matter of fact, a violation of the rules, to get a dose for no reason. So if you're strolling by a box with milligram quantities of californium in it, you actually get a dose just walking by it. So by putting this rather thick, 3-inch thick lead wall in front of that, we eliminate that kind of thing. These are the lengths that you have to go to, but at the end of the day, if you factor in one other feature, and that is scale, so that's 5 milligrams of californium-249 dissolved in about 30 microliters. So it's a little BB, 30 microliters of water. It's a little BB droplet in a Teflon cup for a hydrothermal reaction. And that really is glowing, exactly. We'll talk about that glow in a minute. So that, the real name for that is radioluminescence. So it's lighting up all by itself. That's actually berkelium-249, which is a very unstable element. It suffers from the fact that it has an odd number of protons, and its sum of protons and neutrons is also odd. So these so-called odd nuclei, with 4 exceptions, are very unstable. So the half-life of that is only 330 days. So there's a real question when you're dealing with a half-life like that, can you even grow a crystal? And if you grow that crystal, does it self-destruct because of radiation damage before you can ever collect any data, let alone structural data, which tends to be among the longer data collections? But if you then scale down all your reactions and you build these kinds of very intricate facilities, we can do exactly what everybody else in this room does, which is grow crystals. This is actually not a radioactive sample, but this brings up another point. You don't go in the laboratory and say, I want to make a californium compound today. There's a lot of work with either less radioactive or non-radioactive elements in which we refine both the synthesis and crystal growth so that it will work on the very, very small scales that we have to work on. And perhaps most importantly, that the crystals will grow, we really need them to grow in hours, sometimes minutes. And so there's a lot of work that goes into achieving very rapid crystal growth. But so in this case, this is a samarium compound, which happens to possess a very similar standard reduction potential to californium, so we use it as an electrochemical mimic for californium chemistry. But that's a nice example of work that we have to do before we do the radioactive work. So one of the ways of illustrating how poorly these elements are known is simply to go into both, this is both ICSD and Cambridge databases combined, and look at the percentage of the single crystal structures that are for each of the known actinide elements for which structures have been reported. And not surprisingly, the 2 that are naturally occurring in the Earth that have multi-billion year half-lives, uranium and thorium, those dominate the crystallography. And the reason why uranium is much more prevalent is both because it has much more applications than thorium, but also because it's redox active. Thorium compounds are almost always thorium-4. This unfortunately has led to thorium being neglected. I think people forget that it is the largest +4 cation and therefore has really unique coordination chemistry, even if it's not very redox active. So what's changed? I've kept this pie chart basically the same for about, I don't know, at least 15 years, is the number of structures in these wedges. So the really neat thing that has occurred over the last 20 years is, one, the national labs have reinvigorated their own synthetic transuranium facilities. So if you go to Los Alamos or PNNL or any of the other national labs, there's been a rededication to this kind of chemistry, with new facilities, new instrumentation, and most importantly, young scientists, which really hadn't entered the field for quite a long time. And the reason that that's true is that there's also been a rededication by the university. So, I was probably the first new sort of radiochemistry focused person to come online in 20 years when I started my lab in 1998. And since then, there are probably 20 more labs that have come online just in the United States. And so that's allowing a workforce development to occur, and that's what's making possible the national labs to do this kind of work, again, with a heightened focus. So when I put together this pie chart, there were probably 50 neptunium structures, about 50 plutonium structures. These are now about 400. So that's how much this has changed in less than 20 years. This, when I started putting this together, was about 2,000, and now it's about 10,000. Okay, so there has been an enormous amount of new structural information that has become available just in the last few decades. Some of that is because of the return of interest in nuclear energy, the return of interest, unfortunately, in our nuclear deterrent. But some of that is also because of the changing technologies that has occurred in X-ray diffraction. Almost everything I'll talk about today is not possible on the kinds of diffractometers that I used as a graduate student. Data collection is too long, sources are too weak. They would all fall apart long before we could collect the data. Now, another point I want to make, I already mentioned how unstable berkelium is. This 0.01% is one structure. So if you, 10 years ago, if you went into the Cambridge database and just put in berkelium, that's the only thing you needed to put, a single structure would pop up. It was the tris cyclopentadienyl complex of berkelium-3. You could use the very nice CSD graphics and tumble that molecule around and really look at it. That molecule doesn't exist. It didn't exist then, it doesn't exist now. If you look at the reference at the bottom of the paper and go find that reference, it's a synthesis of that compound. There was a subsequent paper that reported the structure factors with no refinement. The reason for that is they couldn't refine it, because that was done on a picker diffractometer, which is exactly what I was trained on as a graduate student. It would have been a multi-week data collection. That sample wasn't, at the end of that data collection, what they started with. The reason I bring this up is that just because something is in a database, like this compound, doesn't mean it exists. And that's an important lesson when you're doing these large database searches, is make sure those things are real. Now, where can we go to in the actinide series? So thorium and uranium compounds are not going to decompose unless they're air sensitive or thermally unstable on any sort of time scale you have to worry about. But all of the others are going to suffer from this, because when you move to the trans-uranium elements, you no longer have these multi-billion-year half-life. Neptunium-237, which is the only isotope you're going to get a hold of for neptunium, has a 2 million-year half-life, and that helps. Samples typically last for many months, but they will eventually decompose. For plutonium, you're never going to get that isotope, but it would be wonderful. But you can get a hold of plutonium-242, and those samples will typically hang around for weeks to months. But when you move to americium, you are going to use americium-243. That half-life is now 7,000 years. You'll be lucky if that sample hangs around for a week. More likely, it's going to be a nice single crystal for a few days. When you move to curium, now you're dealing with nuclear instability problems. You're going to be working with curium-248, which is an 8.3% spontaneous fission branch. Fission is extremely energetic. It is really bad on crystals. And so you're going to need really rapid data collection. I already mentioned the problems with berkelium. But there's another problem that's been creeping up. Even though when you get to californium, you still have a relatively long half-life for 249 of 351 years. That is the last element you can get 1 milligram of. So this means you're at really small synthetic scales. In addition, you are dealing with really intense gamma rays. Californium has a very abundant 388 keV gamma line. That means you're wearing lead vests. That means you're timing procedures so that you're not getting overexposures. That means you're changing out researchers. A lot of my research group is up here. You're only doing this in large teams. So someone might spend 15 minutes doing one procedure, another person goes in and spends 15 minutes. When the samples come out, those crystals get subdivided. They head to all of the instruments simultaneously. So that takes a big team to put together. Some of these papers have 30 different authors on them for a reason. Now, when you get to einsteinium, we're down to the most einsteinium that the high-flux isotope reactor makes at Oak Ridge National Lab. Every 2 years a batch comes out, is 1 microgram. And there's a battle for that quantity because that is used for the synthesis of new elements. So they're trying to make elements 119 and 120 with einsteinium targets. I want it for chemistry. The nuclear physicists want it for making new elements and for other things. So we only get a fraction of it. The largest fraction we've ever received is 400 nanograms. So this is a whole nother question. Can you grow any crystals with 400 nanograms of materials? Okay, and the half-life is only 260 days. So can you grow crystals with 400 nanograms of material that last long enough for you to characterize? So I'll answer that in the talk today. The last element you can make in a nuclear reactor is fermium. You get 1 picogram of this. That is not enough for traditional synthesis, but there are techniques. I spent a lot of 2020 in Germany on a special mass spectrometer at the University of Mainz collecting data on fermium compounds. But this conference is perfect to be talking about this. Advances in electron microscopy are almost certainly going to allow for a lot more structural data to be collected on einsteinium. And so I hope to be showing you that in upcoming years. Okay, so one of the challenges that we face in the F elements is actually a re-education challenge. So when I was learning about the F elements as a graduate student, I was told these are purely ionic systems. Basically, a +3 lanthanide is just a +3 sodium. Okay, and that there's no ability to control the chemical interactions between the metal ion and the ligands. One of the other transformations that has occurred over the last couple of decades is we now understand that that information that was being conveyed to students is wrong. So the frontier orbitals, of which there are many, so for an actinide you have 5 F orbitals, 6 P orbitals, even though you might say to yourself, that's part of the radon core. You can see the 6 P orbitals from the radon core actually have greater radial extension from the nucleus than even the 5 F orbitals. So these so-called semi-core orbitals have to be considered when you talk about bonding. What I've left out of this, in order not to make this too messy, is you have a 6D orbital, you have a 7S orbital, and a 7P orbital. All 5 of those we'll just call the frontier orbitals, and all 5 of them can and do get involved in bonding. Now, the question still remains is, can we control that? So we've established, using both computational work and experimental methods, that they are involved in bonding, but we are nowhere near where transition metals are in order to be able to control that with a high degree. Okay, so there's a lot of unanswered questions. Okay, so let's start on some of the experimental work that led us down this rabbit hole. So back when I was at the University of Notre Dame, I had this really extraordinary graduate student named Shihua Wang, who convinced me to do something that I had absolutely no interest in doing, and that is to work on low oxidation state actinides. There's a lot of reasons for that. There was ligand K-edge data being, that effort was being led by Dave Clark at the time, now by Stosh Kazimor at Los Alamos, that suggested that as you lower the oxidation state from +6, which is normally the maximum oxidation state for the majority of actinides, to +3, that the degree of frontier orbital involvement decreases. Okay, so in other words, the +3 actinide should be the most ionic. Okay, and therefore, from the ability to control spectroscopic features via ligands, they should be the least alterable. Okay, so that led me to believe there's no reason to do this. We need to stick with +5 and +6 that are the most prevalent ones. But Shihua was convinced that the +3s wouldn't do that, and that they would in fact display non-lanthanide chemistry. And so we, first of all, you can't go to Aldrich and buy plutonium trichloride. So plutonium trichloride, especially, this is with plutonium-239, which means this is weapons-grade material. This is actually comes from the recycling process. So warheads have a shelf life; they spoil, and so you have to recycle them. And part of that recycling process involves the generation of plutonium trichloride. It just so happens that my very first PhD student was now she's a high-level manager at Los Alamos, was in the facility that made it. So we were able to get them to send us a very small quantity of this material. But this also meant building new facilities, because plutonium-3 is slightly air sensitive, unlike trivalent lanthanides. And unlike the heavier trivalents like americium and curium, this will oxidize to +4. So now we needed, our glove boxes have the gloves sucked in. They're under negative pressure because remember the inhalation hazard. So we need to somehow make negative pressure glove boxes also inert atmosphere. This is all non-trivial. So like each of these things that, you know, for transition metal chemistry would be just totally normal chemistry. This is hard with transuranics. So anyway, the point of this reaction series is that if these elements display lanthanide-like chemistry, we should really see one product as we go down this series. Maybe because of the actinide contraction, there's an actinide contraction just like the lanthanide contraction, there would be a phase transition as the result of the shrinking ionic radius. But what you see is none of these are the same composition except for these two, and these two don't have the same structure. So they are polymorphs of each other. I'll only be talking about this compound in detail. This is basically a much lower symmetry form of that structure. But the rest of these have very different compositions. They have different local coordination environments around the metacenters. And with the sole exception of this compound, which are actually those crystals right there, none of these have lanthanide analogs. And that was a really big deal because the folklore and the modern data, the ligand KH Zanes data, suggested that because the bonding was supposed to be so much more ionic, that these should be lanthanide-like, and yet they're not. Okay, so that is really what caused us to start pursuing these heavier and heavier actinides, is there was major departures from what everybody thought the chemical behavior of these elements was. Okay, so but we have to identify why that's true. So we got these clusters of really tiny plate-like crystals of the californium borate. The largest one we could find was 13 by 11 by nothing. Okay, so you could not measure the plate thickness. Now, this is one time when all of the challenges of working with the highly radioactive elements really comes into play. I have 98 electrons to scatter those X-rays. So in fact, we got like a 2.6% R1 on these nothing-sized crystals on an instrument, on the older microsource instruments. So a lot of things came out of this. First of all, the californium structure is layered. There's a reduction in coordination numbers, so the californium here is in a distorted square antiprismatic environment. If I go to any of the earlier actinides, they're 9 and 10 coordinate. We now know, and what the cool thing is when I say we, I don't mean my group, I mean we as an actinide community worldwide, through all of those efforts have shown that Californium's preferred coordination environment is actually 8. It is the place in the actinide series, much like at gadolinium and the lanthanide series, where the coordination number drops. They're not dropping at the same ionic radius, and that's also telling you something fundamentally important about the bonding. Now, even though this is a crystallography meeting, and my group is a very heavily crystallographic group, that is actually not the big deal. That's the big deal. So it was known since the mid-1950s when they could only prepare it was like half of a microgram of isotopically impure, so there'd actually be 4 californium isotopes. Those sub-microgram samples glowed green. Now that's not that unusual when you have short-lived radioisotopes. Short-lived curium isotopes do the same thing. Curium-242, curium-244, those samples will light up orange. And if you collect that photoluminescence spectrum, I'll show you this. You get a very sharp, very narrow peak width at half mast, sometimes it's less than a nanometer peak. That is a very classic F to F transition. Now this has a much more complicated electronic structure because curium is F7, this is F9. But you could pick a certain excited state and find a gap that would be in the green, and so they said, okay, this is an F to F transition. It turned out there was no modern collection of the photoluminescence of californium compounds. There it is right there. The peak width at half mast is 137 nanometers. It has oscillations in it, and you're looking at stacking because we've collected the temperature-dependent spectrum. It may contain multiple components. It sure looks like maybe there's a peak there, maybe a peak here. This is nothing like what people thought this was. And it turns out what it points to is that californium is actually displaying a kind of chemistry that does not occur earlier in the actinide series. It is a transitional element, much like plutonium, where the fundamental chemistry alters. Okay, and I'll discuss why that's true as we go on. Okay, so whenever you see fundamental changes in electronic structure from what you thought, the first thing you should go to is magnetic susceptibility measurements. So I've included susceptibility times temperature versus temperature, as well as inverse susceptibility versus temperature. This is how I think of things, because this follows Curie law. You should have a straight line with an intercept through 0 if this is a purely paramagnetic system. And here's an important time to have the lanthanide analog. The element directly above californium in the periodic table is dysprosium, so another F9 system. That is actually magnetically well behaved. So we've measured many dozens of dysprosium samples. You do get a nice straight line, and you can calculate what the free ion moment should be, and it's about 10.65 more magnetons. And if you've done a good job measuring the mass of your samples and you do a full fit to your data, you're going to get something very close to that theoretical moment. So if you do a full fit to this data, you get 6.7 more magnetons. It's a 40% moment reduction. It's not even vaguely a straight line. It turns out this curvature is caused by massive splitting of the ground state. But if you look at the magnetic saturation, you see a similar effect. So dysprosium samples, the reason why your neodymium iron boride magnet, if you have a hybrid vehicle or get power from a windmill, or use earbuds or a cell phone, all of those have those ultra hard magnets in it. 20% of the neodymium has been replaced with dysprosium to make them a stronger magnet. And you should be saturating up here at about 8 more magnetons. This is saturating at 2.5 more magnetons. So far, there are no similarities between the electronic properties of californium, an F9 system, and dysprosium, an F9 system. And we'll need to address why that's true. So, one of the reasons it's true came out of these quantum mechanical calculations that were run by Laura Gagliardi's group, now at the University of Chicago, but then at the University of Minnesota. And what I'm showing here are the 7 F orbitals. But this is a case that if I were to do this correctly, first of all, I would violate the rules and put up some ugly table, because that's what we need to do. Every single frontier orbital is involved in bonding in the system. So all of these F orbitals are acting as acceptor orbitals. This is the 7p orbital, very heavily hybridizing with oxygen 2p orbitals from the borate. Okay, so all of the empty orbitals act as acceptor orbitals, even the partially filled ones act as acceptor orbitals. The californium oxygen bonds are overly contracted. What that's telling you is this is a covalent system. As a matter of fact, it's a very covalent system. So in the place in the periodic table where predictions were, because of the actinide contraction, among other things, that the elements should be very ionic, we are seeing the exact opposite effect. Okay? So, again, we need to answer why that's true. And the first thing you need to do is address the problem that if I were to go back to that borate structure, especially if we looked at the layer, the world doesn't, it's weird because most of what we use technologically are not molecular materials. They're some sort of extended structure. But we think about chemistry in terms of molecules. But there's a legitimate worry that it's the band structure of that borate that's unusual, and it has nothing to do with californium specifically. In other words, we just have some sort of really exotic compound. The way you solve that problem is to move to a very well understood ligand. This is called dipiclinic acid. It's been known for well over 150 years. And it turns out to be a remarkably good chelator of both lanthanides and actinides. So its binding constant to europium 3+ is 10 to the 8th, for example. So for such a simple ligand, it's really good chelator. As a matter of fact, its derivatives have been proposed in some of the procedures for recycling used nuclear fuel. What's really nice is that if you use an excess of this with californium trichloride, you should be able to drive this to a tris chelate. If you do a very mild hydrothermal reaction, this is done on a 4 to 5 milligram scale, so a really small scale, you actually grow really nice blocky crystals. These are about 30 microns. We don't want them any bigger than that. The reason is when the alpha decay occurs, you want the alpha particle to get out of the crystal and not deposit all of its energy in the crystal. So that's going to reduce some of the radiation damage to the sample. Now, even with that, that's what the crystals look like a week later. And this is a particularly stable californium compound. It's well known that dipiclinic acid is unusually thermally stable and unusually stable with respect to radiation damage. It's not most organic ligands are not like that. So you get these nice crystals. This, by the way, still produces a reasonable diffraction pattern and refinement. You get like a 5.2% R1 from this, but you could imagine that if I'm not measuring crystallographic features, but instead of optical features, that red crystal is a problem. So the red color comes from the displacement, probably of oxygen atoms in interstitial sites. Those are called F centers or colored centers. That is a much more intense absorption feature than anything we'll get from the sample itself. And so if I measure the optical properties of this, I'm measuring the optical properties of defects, not the optical properties of californium diberylate. But my favorite thing about this synthesis is this is the crystal structure. I mean, did you ever think that even for a very simple molecule that you could say, I'm going to make a tris chelate of element 98, okay, and get it? Well, that's the structure. So, as with all tris chelates, they're chiral, so it doesn't matter that this is a tricap trigonal prism. Instead of an octahedron, it's still chiral. This actually has two molecules in the asymmetric unit, but it crystallizes in the centrosymmetric space group, so it's a racemic mixture of both enantiomers, but still, it was a wonderful structure. But the more important thing that came out of this will go forward. There we go, it's just a big slide, is actually the optical properties again. So we have what's called a microspectrophotometer. So big Zeiss microscope, big CC detector on the top of it. And we can collect transmission, absorption, photoluminescence, and Raman on samples down to 5 microns. Which means if these crystals, you can actually see the scale bar here, there's a pretty big crystal. We can actually zero in on just a part of this crystal if we want to, or we can collect the whole thing at once. Now, the reason why you're seeing this video and suddenly these cracks occur is one of the keys to not dispersing radioactive materials when we have crystals that are always in oil. It doesn't matter if they're air sensitive or not. That oil in this case is Krytox, one of the Krytoxes, which freezes at negative 130 degrees Celsius. If you're going to collect photoluminescence data, you actually do want your sample frozen into a glass. So this is super convenient that Krytox freezes into a very nice glass. So the reason that it looks like you're seeing this get brighter and brighter and brighter and brighter, and then the cracks occurs, it's now in the glass. And you're seeing that same thing right here, brighter and brighter and brighter, freezes, you get basically a 200% increase in intensity, and now you really resolve things much better. So these are much better crystals than we got for the borate. And now we understand what's going on with the photoluminescence much better, and using other spectrometers that don't have this optical cube cutoff that we have on this instrument, we know this is a Gaussian-shaped peak. And what's really neat when you do this kind of chemistry is I can have the elements on the product side of the equation that aren't on the reactant side of the equation. So the alpha decay product of californium-249 is curium-245. That is actually the most luminescent F element that there is. That peak at 611 nanometers is photoluminescence from about 1 part per million curium-245 in the sample. And what's really nice is this kind of gives you an internal standard, because you can compare the peak width of that, which is very narrow, to the peak width of this, which is 125 nanometers, and convince yourself that this transition, the broadband transition, is not an F to F transition. Okay, so in addition, we also measured the magnetic susceptibility. It has a reduced magnetic moment from that you would observe with dysprosium. And now we have something else that's really wonderful. In the case of the borate, we can't make an isomorphous dysprosium compound. Dysprosium makes a completely different structure. In this structural series, we can make every lanthanide and every actinide with the exact same structure. So we don't have to worry that there's a change in structure type that's messing around with the physical properties that we're measuring. We don't have to worry that when we make bond distance trends that some sort of transition in structure has caused a discontinuity in that. These are all isomorphous series. So let's explain some of the things that are going on. One of the nice things we can do is we can make the pure curium compound, again, isomorphous with the californium compound. And that spike that I showed you in the previous spectrum, that's the spike right there. It overlays dead on with the pure curium compound. So we can convince ourselves that that is really curium-245 in the previous spectrum. Here's the broadband spectrum, here's the oscillations. We can assign in the absorption spectrum all of these F to F transitions. but there's a broadband transition that's coming out of the near UV that we now understand as a charge transfer transition. So in the ground state, this really is californium-3, but that broadband transition is a ligand to metal charge transfer transition, which are broadband transitions. They commonly have vibronic coupling, and if you want to convince yourself of that, just go grab some potassium permanganate, make a dilute solution, throw it in your UV vis spectrometer, and you'll see really nicely vibronically coupled absorption features. Actually, one of the classic ones. We can calculate the vibrational modes. That's actually what we're doing here. And it turns out there are 5 features that you should be able to see that are all variations on a theme. So this is a pyridine ring of the dipeptylenate, and it's undergoing a breathing mode where it's elongating along this nitrogen-carbon axis. When that nitrogen atom pulls away from the californium center, that oxygen atom of the carboxylate pulls into the californium center. And that has a frequency of about 600 wave numbers. So then you can do single crystal Raman spectroscopy and see if that vibrational mode is there, and lo and behold, it's there. The other thing that you can do is collect excitation data. So in an excitation spectrum, you hold your monitoring at the peak lambda max wavelength, and you scan to find the excitation features that are responsible for this photoluminescence. So if you take the berkelium system and you scan through, all you find are these well-known F to F transitions that are giving rise to the photoluminescence at 611. So these are all narrow features. If you hold this at 525 nanometers and scan through, you find a broadband transition for the californium. So fundamentally very different from each other. The reason that this is occurring is for reasons that are not fully understood. This is the first place in the actinide series where the reduction from 3 to 2 is actually pretty easy. It's actually the same as it is for samarium going from 3 to 2. That's what's driving the ligand to metal charge transfer. What it's telling you is the californium is trying to reduce, which incidentally, I don't have this in my talk, but that gave rise to a 7-year, very difficult quest to prepare authentic californium-2 compounds, which we only managed to pull off last year. So there are other reasons, though, that we're observing large deviations in the magnetism than just covalency will cause reduced magnetic moments because you're delocalizing the spin density out onto the ligands, okay? Charge transfer will cause changes in magnetic moments, but it turns out you don't even need to invoke that to come up with gross changes between the behavior of lanthanides and actinides. And that's because actinides are under really firm relativistic control. So spin-orbit coupling scales as nuclear charge to the 4th power, so Z to the 4th. So it's a strongly nonlinear phenomenon. All of you, when you took general chemistry, learned Hund's first rule, which is that the lowest energy bound state is the one with the highest multiplicity, which is don't pair your spins, right? So let me show you why we can get strange magnetism from actinides without worrying about the covalency problem. So in gray, I have gadolinium-3. This is an F7 system. It's in MRI contrast agents, for example. And you can see what I'm plotting here is adherence to it being spin up. And we didn't lie to you when we taught you general chemistry. It is really all spin up. Now we're going to move on to curium. So what happens? We're going to just directly below gadolinium to curium. The magnitude of spin-orbit coupling has gone from about 0.7 EVs to about 1.4 EVs. So that's a really large jump. But still, the deviation, these are your angular momentum quantum numbers. I'm putting this in blue. If we take the worst case scenario, and notice that I'm only plotting from 70 to 100 here, we go across, it's still like 92% spin up, 8% spin down. So you have a quantum mechanical admixture of the two. So the first thing we need to recognize is why that's occurring. Hund's rules, there are actually 3. Unfortunately, we only teach one, the first one to chemists. Relies on an assumption that the magnitude of electron-electron repulsion is much, much larger than the magnitude of spin-orbit coupling. That's not true in the actinides. Okay, so it's not that Hund's rules are wrong, it's that the assumption that they're based on has begun to fall apart in really, really heavy elements. But then remember that this is scaling non-linearly. So if we look at berkelium 4, that allows us to also maintain the F7 configuration. That's in red. And because I like to engage in hyperbole, I left this one off intentionally. It's actually down here. This is only 60% spin up and 40% spin down. That's a really large breakdown in how we think about pairing our spins and our ground states. That alone will create very large reduction in magnetic moments. Okay, so now let me return back to a slide that I had earlier and rediscuss the challenge that I said that still remains, is can we gain any degree of control of the degree of covalency like people do routinely with transition metals? So one of the ways that you could do that is you could say to yourself, okay, ligand orbitals are coming in, they're just barely overlapping with the 5f orbitals. These are the ones we really need to target because that's where our unpaired electrons are, so they're going to control the majority of the physical properties we want. Well, if I could just push the ligands in closer, that would be really nice. Well, of course you can. You can do that with a diamond anvil cell by going to very high pressures. You can say that in 1 or 2 sentences, but doing that in the lab, getting good at it, has taken us an entire decade. So 2 entire PhDs, one of those is here, he's now a postdoc. It's taken a lot of work to pull this off. So just to give you a scale, and incidentally, I'm going to blame this slide on said postdoc, and I've cleaned it up quite a bit. I took this from one of his group meetings. But we talk about these pressures as if we understand what they mean. If you squeeze your fingers together, that's about 32 kilopascals, and that tells you immediately the pascal is a very small unit. Okay, so that's not a ton of pressure. If you go to like a stiletto, the 1 square centimeter point there, remember you're taking the person's entire mass and squeezing a lot of that mass down to the little area. That's actually about 10 million pascals, 10 megapascals. One of the things to remember is that when you grind things, you actually generate a lot of pressure. So in a mortar and pestle, you can generate up to 2 GPa just by grinding on things. And I remember as a graduate student, just before I arrived, we have Carla in the audience, so you probably overlap. One of the solid state students was grinding a sample and his powder pattern kept changing, and he was inducing a phase transition by grinding up the sample. Okay, so you actually can make a lot of pressure because you have actually a fairly small contact area between the pestle and the mortar in your sample. If you bite down on something, you actually are generating about a megapascal, and a firearm can generate hundreds of megapascals. So on a grander scale, if you really want to cause significant changes in chemical bonding, you need to go up to the gigapascal scale. For transuranics, the highest pressures we've gone to so far is 31 GPa. I have a student that's doing a lot of lanthanide work right now. I think he's broken 40 GPa, and we're waiting on equipment to arrive, which we'll have to build and learn how to use. That'll go up to about 150 GPa, because we have some very cool things coming in the future. Researchers have gone as high as a terapascal using diamond anvil cells. That's about a quarter of the core of Jupiter. And you can see if you really follow the scale up to the pressures in neutron stars and black holes, you have really, really high pressures that cause the fusion of protons and electrons. Okay, the basic principle I think is very well understood, is that you're applying pressure here and here to a much narrower region. This seems like an easy thing to do, put a single crystal into some kind of pressure transmitting media, have an internal standard, which is usually the fluorescence from ruby because it tracks really nicely. With pressure, you'll have a gasket, so this is a little donut with a hole in it, that your sample's contained in, and then you have a cell that allows you to push these together. What's really nice is if you go to the expo, there's quite a few vendors that are selling different kinds of high pressure equipment, and all of the big single crystal companies will now sell you high pressure capabilities with your instrument right when you buy it. My warning to you is what I just said. It took 5 years for us to do this competently, and I would say 10 years to do this well. High pressure single crystal structures are actually really difficult to do. A lot of samples don't remain single crystals as you pressurize them. Even if you don't have phase transitions, they'll crumble and become microcrystalline. Some of them will become amorphous. But the other thing is, you have to process this data, and that turns out to be challenging. So in high pressure crystallography, you're going to start off doing the normal things. You're going to zap a crystal with X-rays, use your air detector to detect diffraction, rotate it around to get a hemisphere, a sphere of data, or whatever collection routine you want. In high pressure crystallography, this goes between two diamonds. And those are, of course, single crystals, which means those are going to diffract just fine when you hit them with X-rays. You're going to put in a gasket, which usually this is steel. If you're doing really high pressure experiments, you're moving to usually rhenium. That's polycrystalline, which means you're going to get rings, right, on there too. Then you're going to throw this in a steel cell. This is thick enough that will completely absorb your beam. Then you got to throw in a ruby. That's also a single crystal, so that's going to diffract. You're going to hit this with X-rays. Some of those X-rays are going to hit your cell, okay? You're also going to get diffraction from all of those different features I just described, and then, of course, you're going to move this around. So what this creates in real time is something like this. So if we look this real time, see that shadow that moves across and ultimately wipes out the entire screen? That's the cell moving into view. You'll notice that this is a very nicely diffracted crystal, but here and there you see these really intense peak spot. That's diamond and ruby, okay? You have to account for all of that, and if you do that, unfortunately, because of the absorption of the cell and everything as I've talked about, you don't end up with a sphere of diffraction data, you end up with this torus, this thick discus. There are ways of dealing with this. If you have the luxury of choosing your structure type, which sometimes you do, if you get a very large unit cell that is also very high symmetry, and by the way, that's usually mutually exclusive from each other, but there are certain examples of that, then you have a lot of redundancy in your data, and it doesn't matter that that's what you're getting, you still have all of the reflections. The other thing you can do is move to short wavelengths. So our new instrument, which we just set up a year ago, after I moved here to Colorado, we have a silver source, and the new Diamond 2 silver sources from Buerger for the first time, those are really bright. Okay, and that leads to much higher data completion than you would have with a molybdenum source. So this has made our lives much, much easier. Okay, so let's just do one high pressure experiment to close out this talk. I have a bunch more data if you guys want to be here for 2 hours, but I'll just do this one. So we're going to take a curium compound, and we're going to bind it with a dithiocarbamate. So this is actually a heavily delocalized structure because those it's all delocalized between the sulfur, the carbon, and the nitrogen. This negative charge is spread out all throughout that. And the first thing I need to tell you about a structure like this is this wasn't chosen randomly. Yes, you can take everything you make and pressurize it, and we kind of do that in the lab. Whenever we have these really exotic samples with these very special elements, we say the same thing to ourselves. This may be the only time in history this compound exists. We need to get every kind of data that we can possibly get in our laboratory right now, including high pressure data. That's kind of mindless for high pressure work. What you really want to think about is what's going to give you the largest responses. So the first thing you need to think about is the energy difference between the metal orbitals and your ligand orbitals. And it turns out there's pretty good degeneracy, energy degeneracy, between the sulfur 3p orbitals and the curium 5f orbitals. That's good for forming covalent bonds. The second thing you want to think about is that if you pressurize a soft donor ligand that is also delocalized, this probably will give rise to a large pressure response because the pressurization will polarize that electron density. Okay, that's why this system was actually chosen. What was really nice, and we didn't know this a priori, is this has gorgeous photoluminescence without any pressure. So you resolve the ligand field splitting, so this turns out to either be the number 2 or number 1 largest ligand field splitting. It's about 1,000 wave numbers. That's actually pretty big for an F-element system. That's actually another thing that has come out of this work is we now know that the later actinides have quite large ligand field splitting. So it should have been the opposite of that, but it's actually fairly normal now, we know with the heavier elements. Now, what happens if you pressurize this? So this is the black spectrum at 0 GPa. We're going to increase this to about 1, and then 4 and 5. We're going to go almost to 11. As this peak broadens out, its intensity really drops. The question is, why is that occurring? But we need to back up just a little bit and reinforce one statement, which is this is an F to F transition. Okay, this isn't a charge transfer transition. So if we can get the F orbital involved to a greater degree in bonding, you might anticipate there being vibronic broadening, just like you would have with transition metal complexes. That's exactly what you're seeing here. So if you examine the wave function for the curium-sulfur bond, and you ask yourself, what is the composition of that bond? What you find out is that it is mostly sulfur 3p in character, but as you pressurize it, what you do is you double the amount of 5F characters. So you go from a very small contribution of less than 1% to still a small contribution of 2.5%. But that doubling of the 5F participation results in really large changes in the macroscopic properties of the system. And that's really striking. That was something that I've been trying to hit home throughout my own independent career, is that gaining even small amounts of 5F contributions to the chemical bonds creates gross changes in the physical properties. And so this has continued on. We've produced, well, I'll actually show you this. This is a system that contains hard donor ligands. So this contains carboxylate donors. This doesn't have a large pressure response, just like I was speculating on. And let me move through all of this to here. So if we compare, for example, a neodymium compound, this is with a hard donor ligand, this is a diglycolamide. You pressurize this all the way up to almost 7 GPa, really minimal shifting in the F-to-F transitions of 2, wave number shift, we'll call that 0 per GPa. You move to a really delocalized system. This is malaonitrile diphthalate, which is a soft donor system that is not only delocalized but also redox active. You actually get, for lanthanide, a pretty large shift in F-to-F transitions. But if you move to americium, which is the same ionic radius as neodymium, and you go to, for instance, that same soft donor ligand, you're shifting your F-to-F transitions by 71 wave numbers per GPa unit. So you can actually have really large effects on the electrons in the F orbitals if you choose your ligands carefully. So with that, I want to give you an outlook, and I want to return to the discussion about einsteinium. So pick your ligands carefully, find ones that are delocalized, highly polarizable, have soft donors, and you can have large effects on F-to-F transitions in both lanthanides and actinides, but it's much more pronounced in the actinides. We are routinely going up near 40 GPa now, but we will be able to achieve much higher pressures as well as laser heating. And this will enable us to do synthesis in the diamond anvil cells to actually get exotic oxidation states that you're not going to get under ambient conditions. So give us probably more than a few years. This is going to take a while. Now, let's move on to the last actinides we're going to be able to get any kind of reasonable macroscopic quantity of, californium and einsteinium. One crystal is all we need. Okay, the question is, can you get one crystal with einsteinium? Those dark red crystals are actually an einsteinium dithiocarbamate, tris dithiocarbamate phenanthroline complex, grown with 400 nanograms of material, which then begs the question, how big are those? They're like a micron. Okay, so they're like super teeny tiny crystals. But this is why the technology that we all are considering normal today is so transformative. Our new diffractometer will have no problem with a 1 micron crystal. So at the time we got these, which I think was 2017, I think that sounds about right, the diffractometers, they're still nice area detectors with bright sources and everything. This, absolutely not. But more importantly, these only hang around for about 20 minutes. Okay, so could you do a 20-minute data collection back in 2017 on a 1 micron crystal in a home system? The answer is no. Now we can. As a matter of fact, at the Colorado School of Mines, where I'm at, all of the students, regardless of major, have to do what's called a summer field session. And I had the physics students come through my lab, and I was showing them our new instrument, and I grabbed one of my graduate students, who's not here, and I remind me to yell at Jacob later. Anyway, so I grabbed Jacob, said, Jacob, go grab a crystal, put it on the diffractometer. And while I was describing it, the structure popped up. Okay, so, I mean, this is like from 2 and 3 week data collections when I was a graduate student to not being able to finish a very short summary of what an instrument does and having the structure pop up. This is really transformative. So you should be seeing einsteinium structures from us in the near future. Okay, so let me thank the research group. I have a wonderful group. I've really been blessed with far more than my fair share of really superb graduate students over the years. But also many collaborators, and I hate these kinds of lists because they always leave lots of people out. And so I really liked what Cambridge did in that point competition. What I loved is even though they left the ICSD out, which bothers me because half of my structure is in there, not in Cambridge, but 330 co-authors just from the Cambridge structures. that is the joy of this work, is that you have to work in really large teams. You get to meet amazing people with amazing capabilities that bring the science to a whole new level. So with that, I really want to thank, there's many agencies that have funded this work over the years, but the Department of Energy's Heavy Element Chemistry program has funded the vast majority of the work I've talked about today. Eternally grateful to them. With that, I'd be delighted to answer any questions.
Thank you for the delightful talk. Questions?
Yes. Oh.
Great talk, thank you. On?
Yeah.
I can be fine.
I really enjoyed seeing this magnetic properties on this material. But I would like to ask a question about the synthesis, from synthesis perspective. There are very few techniques, and one of them is hydrothermal technique to grow actinide crystals, right? If you think about CBT and flux growth, you need a larger quantity of starting material to start with. But in the hydrothermal technique, you always limited with how high in temperature you go, right? Sometimes higher the temperature you go, the larger the crystal you can grow. I see in your presentation the temperature was like 240, which is normal for hydrothermal technique, but same technique you could go for higher in temperature, and I know one group in Clemson does that. Do you
Joe Polis's group. Yeah, so we had all of that, that's Lico Tempress was they are out of business now. They gave us their designs. I bought a billet of Rene 41 that's only made like once a year by one company. We had to buy $3,000 worth of cutting tools from my machine shop, and we made our own Lico Tempress autoclaves. So I've stopped doing that work. So we were taking water to 600 degrees. That's way above the supercritical point of 374 degrees. We were at 40,000 PSIs. There's a real question. We did that with uranium. One of the things we were able to grow is quite large single crystals of uranium dioxide, which we, as a planet, have lost the ability to do that. It turns out that that's important. Those went off to many of our physics colleagues for different kinds of measurements. But those tubes fail a lot, right? So they get little pinholes, and if it's uranium, who cares, right? That's super easy to clean up. It's very easy to decontaminate. If it's plutonium, the world has ended. Okay, so you can do it. Okay, and boy, if the autoclave went off and those go off, then it's really the end of the world. So I think it can be done. Okay, and if I really wanted to do it, we would do it. But you'd spend a couple of years engineering just the safety features of that. So certainly the technology has existed since Bell Labs created the technology in the 1940s, actually. But extending it to really hot elements, you're going to have to really think about. You're going to have to take the worst case scenario, it goes off like a grenade, and reverse engineer from there. So, because as you know, you're at a national lab, that's what you have to do. So we've never done that. We never went beyond uranium in supercritical water. Yeah.
Thank you.
Yep.
Are there other questions? Brent.
Sometimes the simulation is easier than the experiment.
Right.
With these frontier orbitals, I imagine the simulations are pretty difficult to what extent your experiments, very difficult experiments, have value in substantiating simulations?
Okay, so first of all, you need to work with the right theorists, because this needs to be fully relativistic electronic structure calculations using wave function methods. So this needs to be something like CAS-SEF with spin orbit coupling. Maybe you're going to need perturbative theory on top of that. There aren't that many groups that are really good at that in the world. So I actually built my own theory subgroup, and we have those capabilities within the group. We're not that great at it, so we collaborate with all the different groups throughout the world. What's amazing is two things. One is, if you compare the results of electronic structure calculations, high-level calculations, with one another, there's a remarkable agreement with them. And if, for instance, you look at for a geometry minimization using one of these methods and compare that to the crystal structures, there's a remarkable agreement. There's a new method, it's called ligand field DFT. It's being developed in Karlsruhe. And they are able to match our optical data so well, I thought it was fake the first time I saw it. I didn't talk about that compound, but our californium 2 compound turns out to have F to D transitions, and the simulated spectrum and the experimental spectrum were overlayable. I mean, how often, would you have thought that's even possible? But that just tells you how far theory has gone. So quantum mechanical theory in the last 20 years has really become a different beast. And the ability for people that don't know what they're doing, like my group, to run those calculations, that has really improved, right? So there was a really nice article in CNN News that basically said that the modern chemist really needs to be able to do some theory. And so you certainly need to interface with the experts or you're really going to get it wrong. But we can do a lot of those calculations in-house now.
I think we had
I think Cora had a question.
So you were saying that you usually do a lot of upfront work with non-radioactive analogs, but
Right.
then you also commented on the fact that the lanthanides really have completely different chemistry than the actinides. So how do you actually really use that advanced work, and how applicable is it, I guess?
Yeah, so some of the time you do make isostructural series like the dipercolonate. Sometimes you don't, like the borates. It turns out the synthetic conditions for growing the lanthanide crystals, even if you aren't making an isomorphous compound, usually translate directly to the actinides. So even if you're not making isomorphic compounds, it usually works. There are examples where it did not work at all. So the californium 2 that I've been referring to, all of the reductive methods that work beautifully with samarium, Hannah's nodding her head because that's her PhD project, do not translate to californium. Neither does the crystal growth conditions. But more often than not, they do. So we can usually take a lanthanide that either has the same ionic radius or a similar standard reduction potential, do it on a 100 milligram scale, perfect it, scale it down to a 5 milligram scale, perfect the crystal growth. If you then translate to the actinide, something actually cool happens because you have that really small covalent contribution, everything goes better. Your yields go up, your crystals get bigger. I'm sure the number of kcals involved in that little covalent thing is not much, but it makes everything better. So the yields typically get better, crystals better. It's a nice translation. Yeah. Even if it's not isostructural.
Thank you, Thomas, for a great talk.
Thanks.
I think in the interests of time, if Thomas, will you be around for a while, correct?
I will be here today and tomorrow, yes.
So if you've got other questions,